Hi, Chem 101 students. Welcome back for the second lecture of week 10. This is all about the ideal gas law. So in the last lecture, we covered a kind of gas law that can calculate pressures or volumes or temperatures when we had an initial condition and then there was some kind of change. The value of the ideal gas law is that for one particular condition of pressure, volume, temperature, and number of moles of gas, if we're given three of these variables, we can calculate the other one. We're also going to have a couple of related concepts, including Avogadro's law and STP, which stands for standard temperature and pressure. And then finally, we're going to talk about another topic called related to phase changes, including vapor pressure and boiling point, when a liquid boils and becomes a gas. So first of all, let's talk about STP and Avogadro's law. So STP stands for standard temperature and pressure, and standard temperature and pressure is 0 degrees Celsius and 1 atmosphere of pressure. And so I used to work with a high school teacher. She always told her students to imagine a penguin standing at sea level and it's freezing, so the temperature is 0 degrees Celsius, like frozen water, like ice. And so that's one way to remember it. That's what STP is. And what's useful about STP is that for any mole of gas at STP, the volume of that gas will be 22.4 liters if the temperature is 0 degrees Celsius and the pressure is 1 atmosphere. So that's a very useful relationship that you'll want to have in your notes, because if you're given that a gas is at STP, you can very easily figure out how many moles of that gas there is if you're given the volume. Avogadro's law states this. It looks a lot like our other combined gas laws, except it involves a new variable. It is the number of moles of gas. And so it says volume over moles of gas is constant. And remember that this is the relationship here that was directly proportional. So that means assuming that pressure and temperature are constant, if you double the number of moles of gas, if it's at the same pressure and the same temperature, that will mean double the volume of that gas. So twice as much gas will take up twice as much space, assuming the temperature and pressure are constant. Kind of makes sense, right? So if you know the number of moles of gas under these conditions, you can find the volume and vice versa, especially by this relationship. So let's take a look at how this is used. So here's a good related question. How many grams of CO2 fills a 2.50 liter container at STP? Grams. Oh, dang. Okay. Well, we have the relationship that 1 mole of any gas, for example, CO2, is 22.4 liters of CO2 at STP. But that doesn't get us the grams. Do you guys remember? Is there a way that if we get the moles, we can get to the grams? Hopefully you remember from the last exam. We can get between moles and grams using the molar mass, right? So we can first get the moles, and then after that, if we have the molar mass, we can use that to get the grams. So first, let's get the moles. Even though that's not what the question asks for, if we get moles, we can get the grams. So we're going to start by writing 2.5 liters. In this case of CO2. But the great thing about these gas laws is they work the same no matter which gas it is. But I put CO2 just to be specific. We're talking about liters of CO2 gas. And now we have to decide which part of this conversion factor are we going to put on the bottom. Well, you guys already know, because you look here, you know if I'm doing a conversion, that same unit better be down here, right? So boom, that unit's going to be down here. The number that's going to go with our liters of CO2 is going to be 22.4. So we're going to write that there. And then on the top is going to go 1 mole of CO2. And because of that, our liters of CO2 will cancel and we'll get moles of CO2. So let's calculate how many moles of CO2 we've got now. It's going to be 2.5 divided by 22.4. And so to 3 sig figs, we get 0.111, but since there's a 6 behind it, we're going to want to round that 1 up. So it's going to be 0.112, and our units will be moles of CO2. 0.112 moles of CO2. Okay, great. Now we have moles of CO2, and what we want is we want to get to grams of CO2. This is where you still got to remember, even though it was the last test, you got to remember how to go between moles and grams. It's the molar mass. Okay, so if we calculate the molar mass of CO2, it's going to be 44 grams per mole. This is, if you were to look at the periodic table, it's 12 grams per mole for carbon and 16 grams per mole for oxygen. So it would be 12 plus 2 times 16. So to 3 sig figs, it's 44.0. And so now we've got the molar mass, and we've got it to 3 sig figs, which is fine for our data, which also has 3 sig figs. So this is good. So we're going to copy down our 0.112 moles of CO2. And now again, let's turn off our brain for a second and just copy this moles down here for our conversion factor, because we know it's got to cancel. Then we look back at our conversion factor and we say, okay, the number that goes with moles is 1. And the other side is 44.0 grams of CO2. That goes up here. Then our moles of CO2 cancel, and we get grams of CO2. We just got to multiply now. Let's do that. 0.112 times 44. And we get, we'll round this to 3 sig figs. Since that's an 8, we'll round the 2 up. 4.93 grams of CO2. 4.93 grams of CO2. Great. Okay. And so that's how we can use this 1 mole of CO2 is 22.4 liters, or 1 mole of any gas is 22.4 liters. A very handy relationship, as long as we're at STP. That's really important. So if you see STP, be aware that you can use this relationship. Very handy relationship. Here's another example problem. It's kind of like the reverse of what we just did. So it says how many liters of O2 is 89.4 grams at STP. Well, okay. We're going to start with our 89.4 grams, and we're going to want to get moles, because we know if we have the moles, we can convert that to liters. So our plan is basically going to be to go from grams of O2 to moles of O2. And to go between grams and moles, we need the molar mass. We're going to need the molar mass of O2 for that. Then we're going to go from moles of O2 to liters of O2, and that's what we're asked for. And for that, we're going to need to use 1 mole of a gas is 22.4 liters, and we can use that because we're at STP. Okay. So we write down our 89.4 grams, and 1 mole of O2 is 32 grams of O2. 2 times 16 is the 32. Okay. And so we're going to put the gram part on the bottom, because grams need to cancel. So we put grams of O2, and the number that goes with grams is 32, and the other side's going to be 1 mole of O2. So we fill those in, we cancel our grams of O2, and we'll have moles of O2 here. We calculate 89.4 divide by 32 gives us 2.79. And 3 sig figs is good. These both have 3 sig figs. So 2.79 moles of O2. 2.79 moles of O2. Okay, now we got the moles of O2. Now we can use 1 mole of O2 is 22.4 liters of O2 at STP. So we're going to copy down our 2.79 moles of O2 here. Okay, and again, we can always know if we're converting here our moles of O2, that's going to have to go down here because it's got to cancel. So then we look back at our conversion factor and we see the number that goes with moles of O2 is 1, that's going to go here, and the other side is 22.4 liters of O2, that's going to go on the top. Then our moles of O2 will cancel. Whoops. And we're going to have liters of O2. So now we just have to multiply 2.79 times 22.4. and we get to 3 sig figs, 62.5, because we're going to round the 4 up due to the 9, 62.5 liters of O2. 62.5 liters of O2. Okay. And so now we've finished some couple problems using this relationship. 1 mole is 22.4 liters of a gas at STP. Finally, the ideal gas law. So this is the PV equals nRT. It's called pressure times volume is the number of moles of gas, N, times a constant called R, times T, the temperature, which does have to be in Kelvin, like the other gas laws. And where does this equation come from? Let me explain the origin of this equation first. So we have had two equations now. We had P times V over T is a constant. Or in other words, P1 times V1 over T1 equals P2 times V2 over T2. And then we had Avogadro's law, which said V over N is a constant. Now, just like we combine the other equations, notice here N is on the bottom, V is on the top. If we combine these all together, we get the equation P times V over N and T equals a constant. Okay, and this is true because if we remember how we did it before with the combined gas law, if one of these variables is unchanged, we can remove it. It becomes a constant. So if we remove the N, we get P times V over T. Well, that's true, right? We already had that P times V over T as a constant. Let's say the pressure and the temperature are constant. Pressure and temperature are constant. Then those go away, and we have V over N as a constant. That's true as well. And so we have basically an expanded version of the ideal gas law here. What we also had was that at STP, 1 mole of gas equals 22.4 liters at 0 degrees Celsius and 1 atmosphere pressure. And 0 degrees Celsius is 273 Kelvin. So let's say we put these all in and calculate what we have. So for pressure, we have 1 atmosphere. For volume, we have 22.4 liters. For the number of moles of gas, we have 1 mole of gas. And then for the temperature, we have 0 degrees Celsius, which is 273 Kelvin. And this is equal to a constant. And now the big question is, what is that constant? Well, we can calculate it. If we plug in these numbers, the constant, it would be 1 times 22.4 divide by 1, and then divide by 273. And we get 0.0821 to 3 sig figs, 0.0821, and the units here are liters on top, atmospheres on top, moles on the bottom, and kelvins on the bottom. And this is called R, which is the ideal gas constant. And so that is this R right here. And that's where it comes from. So now we've called this constant, we're calling it R now. We're calling this constant R. So we've got, overall, we've got PV over NT equals R. And if we multiply both sides by NT, we get PV equals N times R times T. PV equals nRT. That's this equation right here, the ideal gas law. And so what's a little bit different about the ideal gas law compared to the combined gas law is we're using a constant that has very specific units. Those units are liters, atmospheres, and moles and kelvins. So whereas for the combined gas law, the only unit we were really cared about was temperature. It had to be in Kelvin. For ideal gas law, we need to be very careful about the units because the R that we're going to have available has very specific units. So pressure must be in atmospheres because the R has units of atmospheres. Volume must be in liters, again, because the R has units in liters. So if we're going to use this R, we need to use the right units so they cancel. N is the number of moles. Yes, moles. R is 0.0821 liters times atmospheres divided by moles divided by Kelvin. So that's why we need liters for volume for this equation, atmospheres for pressure, and moles, because we need those units because the R that we're going to use has those units. So any other unit won't be consistent with this constant. Finally, temperature must be in Kelvin, as it always must be for any gas laws problem, because Kelvin is the relationship to molecular speed, which is what we care about when we're talking about these gases. So this is the ideal gas law. PV equals nRT, Puvnert, if you like. And this is the equation that we're going to use if we have 3 of these 4 variables. So if we're given, for example, pressure, volume, and moles, we can find temperature. Or if we're given pressure, volume, and temperature, we can find moles. If we have 3 out of the 4 variables, we can find the 4th. And the way you're going to know that you're going to use this gas law is there's only going to be 1 of each variable. So remember, for combined gas law, we had like a pressure before, which we called P1 or whatever, and then a pressure after, which we called P2. But we're not going to have a P1 and a P2. We're just going to have 1 pressure, 1 volume, 1 number of moles, 1 temperature, because this is going to be for 1 situation, not like combined gas law, we had a before situation and an after situation. Here we're just going to have 1 situation with no changes. That's what the ideal gas law is used for. So here's an example of this type of problem. It says, what is the volume of 3.5 grams of H2 at 745 millimeters mercury and 31 degrees Celsius? So notice this is grams, but we can get this to moles, okay? We can get moles. So we're just going to say this is our moles because we can turn grams into moles, okay? Here, this is our pressure, P, but we need to turn it into atmospheres because right now it's in millimeters mercury. Finally, this is our temperature. We want to convert this to Kelvin, but notice there's only 1 of each unit. There's not a before pressure and an after pressure, or before temperature and an after temperature. We know we're going to use the ideal gas law because there's just 1 of each of the variables, but we're going to have to get them into the right units. We need to have moles, not grams. We need to have atmospheres of pressure, not millimeters mercury. We need to have Kelvin for temperature, not Celsius. So the first thing we're going to do is identify what we've got. So our pressure here is 745 millimeters mercury, but 1 atmosphere is 760 millimeters mercury. So we're putting the millimeters mercury here on the bottom so that they will cancel. And so we're going to be dividing by this, and we're going to get atmospheres. So we're going to have 745 divided by 760. And that is going to give us 0.98, and the unit will be atmospheres. So we've got pressure in atmospheres now. Great. Volume. That's what we're trying to find out. The question asks, what is the volume? N. Okay, so we're going to have 3.5 grams of hydrogen, and we need to use the molar mass of hydrogen, which is 2 grams per mole, because we have 2 H2s, 2 moles of H2, each is 1 gram per mole from the periodic table. So here our grams of H2 are going to cancel, and we're going to get moles of H2. So it's going to be 3.5 divided by 2. That gives us 1.75 or 1.8 moles to 2 sig figs, since the 3.5 had 2 sig figs. Next, temperature, or R is always the same thing, 0.0821 liters times atmospheres divided by moles divided by Kelvin. Always the same thing. But notice the units. Atmospheres for pressure, That's why we needed to calculate pressure in atmospheres. Okay, moles, not grams. That's why we couldn't leave this in grams. We need to use the molar mass to convert to moles. Finally, temperature needs to be in Kelvin. So we're going to take 31 degrees Celsius. We're going to add 273. 31 plus 273, that gives us 304 Kelvin. Now we're ready to go. So because we have one of each type of value, we're going to be using PV equals nRT. What we want is volume. So you can either plug in the numbers first, like we did with the combined gas law, and then calculate, and then do your math, or we can do the math with the letters. And in this case, it's often easier to do the math with the letters. Here, I want volume by itself. So what I need to do is get rid of P. So I can divide both sides by P, like this. Now my pressures are going to cancel, and I'll have just volume on this side. Great. So volume is going to be nRT over P. Okay. So now we're going to plug in our moles, nRT over P. We're going to plug in our moles now. Okay. So that's going to be N 1.8 moles right here. R, always the same thing. This right here, 0.0821 liters times atmospheres over moles over kelvins. Next, we're going to plug in temperature, 304 Kelvin. That's going right here. Then we're going to put pressure on the bottom. That's our 0.980 atmospheres. That's going right here. Now, before we punch in our stuff, we should make sure that the units work out. Did you notice I left all my units here? You need to do the same thing. I insist that you do, so that you can see the units cancel. And I'm going to expect it when you show me your write-out work too. So we can see here moles divide by moles, those cancel. We also have kelvins divide by kelvins, those cancel. Then we have atmospheres on the top here, divide by atmospheres on the bottom, those cancel. And the only unit we're left with here is liters. So, and then we should double check. Is volume something that is in liters, measured in liters? Yes. Okay, so we probably did our math right. This is a great way to check that you did your algebra right too. If the units cancel correctly, then you probably did everything right earlier. Okay, so now we're going to do 1.8 times 0.0821 times 304 divide by 0.98 equals. And so we're gonna let's see, this number 1.8 had 2 sig figs. So if we're looking at sig figs, we've got 2 sig figs right here. This one's 3 sig figs. This is actually known to many more sig figs. If you needed them, you could find them on Google or whatever. This is 3 sig figs. This is 3 sig figs. So my 1.8 has my least sig figs. So my result is going to have to be 2 sig figs. So I would round where the 5 is. Since this is an 8, we'll round up. It's going to be 46, and the unit is liters. 46 liters is our answer. Next, what is the pressure of 12 grams of helium in a 55-liter tank at 25 degrees Celsius? Okay, so again, note here, we've got one value. This is grams, but we can get it into moles. So this is going to be our moles, or our N. This is going to be our volume, 55 liters. 25 degrees Celsius, this is our temperature. And we want to know what is the pressure. There's no before and after here. Okay, there's just one situation. So that's how we know we're going to use the ideal gas law and not the combined gas law. So pressure, we don't know it. We want to get it. Our moles, or volume, pressure volume is 55 liters. And we don't need to convert it because liters is the right unit. our number of moles is not in fact moles, it's grams. So we need to go to helium on the periodic table. If you look, it has a molar mass of about 4 grams per mole. We put the grams on the bottom so that the grams will cancel. Grams of helium divided by grams of helium. That will get us how many moles? 12 divided by 4 is 3. We got 3 moles. Our R never changes, always the same, 0.0821 liters times atmospheres divided by moles divided by kelvins. Finally, temperature. Temperature is 25 degrees Celsius plus 273 so that we make it Kelvin, 298 Kelvin. Notice, temperature is in Kelvin, good. Our moles are in moles, good. Our volume is in liters, yes, and our pressure is going to end up in atmospheres. Now, again, we're using PV equals nRT because we have one amount of each of these variables. We don't have a before and after, so we're using the ideal gas law. We want pressure by itself, so we're going to have to get rid of the volume here. So to get rid of the volume, we can divide both sides by volume. That's going to cancel our volume on this side, and that leaves us only pressure on this side. Great, all we have is pressure here. And the pressure is going to be nRT over V. So pressure is nRT divided by V. Now we're going to start plugging things in. So the pressure is going to be N here, 3 moles. Put that in right here. R, same old constant, 0.0821 liters times atmospheres over moles times Kelvin. And our temperature is going to be 298 Kelvin. Okay. And then volume is on the bottom. That's going to be 55 liters right here. All right. And now it is time to cancel our units first. Before we grab our calculator, let's cancel our units. We got moles on top, moles on bottom. Good. Kelvins on top, kelvins on bottom. Good. Liters on the top here, liters on the bottom right here, those cancel. And we have units of atmospheres. We should ask ourselves, is that a pressure unit? Yes, atmospheres is a pressure unit, so chances are we did our algebra right. Now let's go and plug in. 3 times 0.0821 times 298, and then divide by 55 equals, oops, something went wrong there. I divided by 298. Whoopsie. 3 times 0.0821 times 298 divide by 55. And so again, looking at sig figs, the 3 has 2 sig figs, the 55 has 2 sig figs. Our result needs to be 2 sig figs. 1.3, we round down since there's a 3, 1.3 atmospheres. So 1.3 atmospheres is our answer. All right. And so that's how we do these gas laws problems here. Now let's do one more ideal gas law problem. Okay, so for this one it says, how many grams of N2 gas are contained in a 2.0 liter tank at 1250 torr of pressure and 18 degrees Celsius temperature? Okay, so here we're asked for grams, but we're not going to be able to get grams. What we can get is we can get moles, and then we can turn those to grams. Okay, now we've got a volume here, so we got a volume 2 liters. We've got a pressure, which is in torr, not in atmospheres, but it's right there. And we've got a temperature, which is in degrees Celsius, not kelvins, but we can get into kelvins. And so notice, again, we've only got one of each variable. We've got one volume, one pressure, one temperature. So this is not a combined gas law problem. This is an ideal gas law problem. We got to use the PV, the PV equals nRT. Okay, so for pressure, we need it to be in atmospheres since we're using the PV. Remember, if we're looking back at R has units of liters times atmospheres over moles times Kelvin. So for pressure, we need to have atmospheres. So we have the 1250 torr, and remember torr and millimeters mercury are the same thing. So 1 atmosphere is equal to 760 torr, or 760 millimeters mercury. We put the 760 torr on the bottom so that the torrs will cancel, and I have atmospheres here. Okay, so I calculate that. 1250 divide by 760, and I get 1.64, and my unit is atmospheres. Okay, so we got pressure, it's in atmospheres. Good. Volume is already in liters, it's 2 liters, we're good there. Number of moles, that's what we're trying to find, so we can get the grams. R, always the same, 0.0821 liters times atmospheres divided by moles divided by Kelvin. Finally, temperature is in Celsius, we're going to have to add 273 to make it Kelvin. 18 plus 273 is 291 Kelvin. Okay, and so we're ready to go now. We can plug this in. We've got PV equals nRT. This time what we want is the N. So we have 2 things to get rid of here. We have to get rid of the R, and we have to get rid of the T. So we're going to divide through by RT. Divide by RT, divide by RT. So on this side where the N is, we're going to cancel R and T. That's good. That leaves us with just the number of moles. So the number of moles is going to be PV over RT. So N equals PV over RT. Okay. And so now we're going to plug this in. So I'm doing that down here. We're going to put our pressure. Our pressure is 1.64 atmospheres. We're going to put that in right here. That's our pressure, P. All right. Our volume, we're going to put that in right here. It's going to be 2 liters right there. 2 liters. Okay. R, we're going to put that in here on the bottom. 0.0821 liters times atmospheres divided by moles divided by kelvins. Nice. All right, and now our temperature, that goes in right here, 291 Kelvin. Okay. And now let's check out our variables here, our units rather. We've got atmospheres on top, atmospheres in the bottom, those cancel. We got liters on the top, liters in the bottom, those cancel. We got Kelvin on the top of the bottom and Kelvin on the bottom of the bottom. So that's going to be Kelvin divided by Kelvin, those cancel. And then for units here, we got 1 over mole. So we got 1 over mole. And remember, if you're dividing by a fraction, that's the same as multiplying times the reciprocal. So that's going to be 1 times mole over 1, which is just going to be units of moles. So, and moles is what we wanted. We were looking for moles. So great. Great, this works out. Okay, so now we have to punch the calculator, and here's where you need to be very careful. Remember the same thing I always keep harping on you about. If it's on the top, press times. If it's on the bottom, press divide. Period. That's all you got to do. As long as you do that, you'll get it right. So we're going to do 1.64, then times 2.0, because it's on the top, times 2.0 if you like. Now, this is on the bottom, so we press divide. Divide by 0.0821. Now, here's where people mess up. 291 is on the bottom. Press divide 291. Okay, not times. It's on the bottom. Press divide. And now we're going to get this number, and 2.0 liters had 2 sig figs. That's the fewest, so we're going to round to 2 sig figs. It's 0.14. We round up because of the 7. And our unit is moles. 0.14 moles of N2. Now, are we done yet? No, because we were not asked for moles. We were asked for grams, okay? So we need the molar mass of nitrogen. If you look at the periodic table, 1 mole of nitrogen atoms weighs 14 grams. And you know that 1 mole of N2 has within it 2 moles of N atoms. And so that mass is going to be 2 times 14 grams. And so it's going to be 28.0 grams of N2 is 1 mole of N2. And so that's the molar mass we're going to use here. We've got, so we're going to put that right here, and my head is definitely going to be in the way for this one. So 1 mole of N2, and that is, we put grams of N2 on the top, moles of N2 on the bottom. So moles of N2 will cancel. We'll get grams of N2. And so let's calculate here. All right. So it's going to be 0.14 times 28. And so we're going to round this to 2 sig figs, 3.9 grams of N2. 3.9 grams of N2. And hopefully you can see the mole of N2 past my forehead. All right. And so that's how you solve for the different variables using the ideal gas law. Remember how to decide which you should use, because you got combined gas law, you got ideal gas law. Which should you use? The way that you decide is based on what you see in the question. If it's a combined gas laws question, you're going to see more than one of some variables like pressure, temperature, or volume. If you see a before pressure and an after pressure, or before temperature and an after temperature, that's telling you need to use one of the combined gas laws here. If you see only 1 grams or moles, only 1 temperature, only 1 volume pressure, you're going to use the ideal gas law. And so that's probably the hardest part of these questions, is figuring out which equation you need to use. This is how you figure that out. After that, just make sure you got everything in the right units and plug and chug. All right? A couple of last topics before we finish this section. And these have to do with phase changes, specifically between liquid and gas. So we're going to go over some terminology, including vapor pressure and boiling point. So vapor pressure has to do with the idea that when you have a liquid and you're just leaving it there, on the surface of the liquid, molecules are going to begin to evaporate. So I'll propose to you 2 situations here. Let's say you've got a glass of water, right? And it's open on the top. That's the first picture. You leave it on your desk though for like a few days, maybe a week. You forgot about it. When you come back, the water level is lower, right? But none of the water had spilled out. What happened was, little bit by little bit, the water molecules at the surface of the water, just a few of them happened to escape, and they flew off and they left the cup and they never came back. Because there's lots of places where they could go once they've escaped the liquid here. So that happens all the time. The water molecules will escape and escape until they leave. They all leave the container. Eventually, if you leave your cup on your desk long enough, all the water will evaporate. But it's different if you have a closed container. And this would be like your closed water bottle. So imagine that you drive to school. It's not COVID. Let's pretend like it's not COVID for a second. And let's say you drive to school, right? And so you drive to school, and you have a water bottle. You drank it halfway, and all the water's in the bottom, but you leave it in your car on a hot day. And then you come back after the day's over in the afternoon, and at the top of your water bottle, there are drops of water on the side near the top. Now, no one came into your car and shook your water bottle up, right, and put drops of water on the top. What happened? Well, what happened is your car got hot inside of the course of the day, and the molecules of water got hotter as well, and more of them evaporated. And then it got cooler later on in the afternoon, and some of them condensed up on the top of the sides and made droplets. So what you saw there was the fact that when the water inside the bottle got hot, a greater fraction of the water molecules would evaporate and go from the liquid phase into the gas phase. And because there's a greater number of water molecules up here in the gas phase, that means there's a higher pressure of water molecules in the gas phase. But then when your car cooled down in the afternoon, that number of water molecules that are evaporated went down, and some of them condensed on the side. This is related to the idea of vapor pressure. So vapor pressure is a pressure exerted by the vapor of a liquid above the liquid when they're in equilibrium with each other. And what this means is that there are as many molecules evaporating at any given time as there are those molecules falling back in to the liquid. And as you see with the with the example in your car, vapor pressure is higher when the temperature is higher. Okay, this is really important. There's a higher vapor pressure when the temperature is higher. That is why when your car was hot in the afternoon, there was a greater amount of water molecules up in the top, and then when it cooled down, fewer of them were staying in the top. The vapor pressure was higher. There were more water molecules when the water was hotter than there were later when the water bottle cooled off a little bit in your car, and then some condensed and there was less vapor pressure. So there's higher vapor pressure when the temperature is increasing, or when the temperature is higher. Sometimes even the bottle will blow up and some will escape because it's got a little bit of leak in the cap. And then when you get back to your car, the bottle has like crushed itself a little bit. This is because in fact the vapor pressure got really high and some leaked out, and then the vapor pressure got lower when the bottle cooled down, and the air pressure outside crushed the bottle a little bit because it was lower pressure inside as it cooled off, which is interesting. That will happen too. And so that's what you observe when you leave that water bottle in your car. Now, the idea of vapor pressure is very closely related to boiling, because as you increase the temperature of your liquid, the vapor pressure is getting higher and higher and higher. And at a certain point, that vapor pressure will be so high that it is equal to the air pressure around. That is called boiling. That is what boiling is. So boiling happens when the vapor pressure of a liquid becomes equal to the atmospheric pressure. And generally we'll boil a liquid like water by increasing the temperature. And once the temperature gets high enough, then the vapor pressure is the same as the atmospheric pressure and the water boils. So the big question is, well, what about altitude? So we said that as you go higher and higher in the mountains, and that's what's represented here, elevation. So as we go higher and higher in the mountains, the air pressure is lower and lower. And what that means is that you do not have to get water to as high of a temperature, because, as we know, the vapor pressure gets higher as the temperature gets higher, right? So and this is a kind of pressure called millibar. In this kind of pressure, 1,000 is atmospheric pressure, okay? Or is 1 atmosphere of pressure, rather. So if you're at sea level, you've got to get water up to 100 degrees Celsius if it's going to have a vapor pressure that is equal to atmospheric pressure. But when you're high in the mountains, the atmospheric pressure is lower. So you don't need to get the water as hot because it does not have to have as high of a vapor pressure to boil. And that has an interesting impact on like cooking, for example. If you ever look at some baking instructions on a box, they'll say, or like cooking pasta, it will say regular instructions and high elevation instructions, right? It will say. And the high elevation instructions will tell you to cook it longer, basically. And this is because this stuff that you're cooking is essentially, if it's very watery, like a cake will be, a cake batter, or when you're boiling pasta like macaroni, mac and cheese, Kraft mac and cheese, the water will be boiling at a lower temperature, and so it will take longer to cook what it is you're cooking because you're cooking it at a lower temperature, the temperature of the boiling water, which at high elevations is boiling at a lower temperature. So what I want you to know about this is that vapor pressure increases with increasing temperature, and boiling is what happens when vapor pressure equals to atmospheric pressure. And that is why boiling happens at a lower temperature at higher elevation than it does at lower elevation. This is also going to be really important when we begin to talk about breathing, because when someone breathes, for example, underwater, they're breathing out of a tank that is high pressure because there's high pressure against their chest as well. And that's going to be really important to divers and to high pressure applications and people diving underwater, and also to the treatment of people that have problems when they dive underwater and have problems because of that, and are treated at a hospital for that. So we'll talk about those type of applications next time. So thank you for joining me, and I'll see you in the next video.